From the first video, you saw, I told you about the derivative of the formula, whereby for EMF of volts, we use what? We use sine theta. Sine theta, of which theta is the angle between the normal line of the loop and the magnetic field line. Remember that we've got two magnets, whereby in those magnets we've got the north and the south. And the magnetic field line are going to move from the north to the south, just like this. Okay, so this is our loop. What I'm holding is our loop, something which I'm using as an example. So you can see that when the loop is parallel to the magnetic field line, the loop is this white metal that I'm holding. The loop, when it's parallel to the magnetic field line, the normal line which I'm representing by this black line which I've marked, you can see that it is perpendicular to the magnetic field line. So let us continue to make a representation of that in the graph. Let me remove what I have on my screen. Okay, I've erased it. So we're going to have our Cartesian plane. Remember that we're talking about an AC. We're talking about an AC generator. Talking about the AC generator, which is the alternating current and the alternating voltage. You know that voltage is going to alternate along here, and I have got very good videos which I'm going to share with you so that you can be able to understand how does the voltage alternate. So here we're going to have the EMF with the SI unit of voltage, and here we're going to have the time. So now I want to make a demonstration because we do not cram the shape of the graph, although we know that as long as it's alternating current, the line of the graph is going to move along the negative and the positive. But when the question comes in the exam, they are very tricky sometimes. They will bring a loop which is in a particular position, and you will need to know where to start when you draw your graphs. I hope you understand that. So, what I am holding here, this white object, I can say it is our loop. Let me erase this so that we can be able to see. So here I'm going to have the two magnets, north, south, magnetic field line going to the south, from north to south. So at this position, you can see what is happening at this position. At this position, the loop or the coil is parallel to the magnetic field line. You can see that they are parallel. You can see here, it is parallel with these lines. But what about the normal line of the coil? The normal line is this one. It is making an angle of 90 degrees. The normal line is in this direction. And that makes our angle to be equal to be 90 degrees. I hope you can see. So, remember for voltage, we use what? We use sine. So it means this time, at that position, we'll have sine 90, which is equal to 1. you can see as I'm representing, sine 90 is equals to 1. So it means that our voltage is going to start from the maximum position. It's going to start from a point which it is high, because sine 90 equals to 1. It is different from that one of current. Then what will happen? Then the loop turns. When the loop turns, we can say that the loop is at 0 degrees. I can draw something that you know, whereby we have 90, we have 0 degrees, we've got 270, then we've got 180 degrees. I can make the drawing to be like that, as you can see. So what will happen now? This is 0 degrees, or you call it 360 sometimes. 0 degrees and 360. Remember that where we start, that's where we end, when we're making a revolution. So we started from what? From 90. The normal line is perpendicular to the magnetic field line. That's why we got sine 90, which is equals to 1, meaning that we're going to start from a high point. Then let us turn our loop. Then the loop turns. When the loop turn is at 0 degrees, and we're going to have what? Sine 0. Sine 0, it will give us a 0, meaning that our voltage at this position is going to be 0. Here we have a 0. Our voltage is going to be 0. It started from a maximum point, then it came to 0. It came to 0 when the loop is like this. When it turned for the first time. Look, the loop turned again. When the loop turned again now, it is pointing here. It is pointing this direction. It means that the loop is at 270 degrees. Then, what will we have? Sine 270 degrees will give us a -1. It means that our voltage is even going to become low. It is going to be in the negative side. It will become lower, you can see. So now, our voltage is in this direction at the 270. Then it turns. Then it becomes what? It comes to 180. Can you see? Meaning that we're going to have sine 180. What do we get when at sine 180? Sine 180 is equals to 0. Sine 180 is equals to 0, meaning that as the coil is at 180, you can see it is pointing at 180. Our voltage will return back to what? To 0. It has returned back to 0. Then return it for the last time, returning it to its original position. We return back to what? To 90. What do we have at 90? Sine 90. Sine 90 will give us sine 90 equals to 1. Meaning that we're going to get our maximum value again. We're going to get our maximum value again. So this represents the first 10. Sometimes they will draw a graph and they request you to tell how many turns did the coil make. This is only one turn. As I told you that the first turn is going to have 5 dots, then the second turn will have 4 dots. So that's how we calculate. That by dots, I'm talking about points. Let us count the first turn. It's going to be 1, 2, 3, 4, 5. You can see that we have 5 points. So it represents that it has turned only once. I hope you understood the EMF time graph for electrodynamics. I can even repeat it again. If you do not understand, let me repeat it again by showing you what will happen. Look at this. Let me repeat it again. I know sometimes it's difficult for some people. people to understand. Let me just repeat it for the last time. I'm repeating it for the last time. This is the EMF. Then this is F.0. It looks like a velocity versus time graph of vertical projectile. Then here we're going to have what? Changing time in seconds. So let us start. Where we will start to draw this graph, it is determined by the position of the coil. If we're going to start from this position, let me draw the magnets. North and south. Magnetic field line from north to south. Then, where we will start to draw this graph will be determined by the position of the coil. This white object represents the position of the coil. So, what will we have? The first thing, we have the coil. You can see that the coil is put in this position. Check the coil. The coil is parallel to the magnetic field line. The coil is parallel to the magnetic field line. But what about the normal of the coil? The normal line of the coil is perpendicular to the magnetic field line. You remember I said that the normal is found in the coil. That's why we call it the normal line of the coil. But it is positioned in a way that when the coil is parallel to the magnetic field line, the normal line is perpendicular. When the coil becomes perpendicular to the magnetic field line, the normal line becomes parallel. When the coil becomes parallel to the magnetic field line, the normal line becomes perpendicular. You need to take note of that when we are told that the coil is parallel, it means the normal line is perpendicular. I hope you got that. So let me just repeat what I've just explained for the last time so that you can understand. Okay? Here is the loop. The loop is positioned in this fashion. You can see the loop, the coil. Let me use the word coil because here we talk much more about the coil rather than using the word loop. Loop is the language we use in grade 11. Okay, here is the coil. The coil is parallel to the magnetic field line, but the normal line is what? Is perpendicular to the magnetic field line. And remember that I told you that since we are having a potential difference graph, the graph of voltage, since we are having a graph of voltage, what will happen? It means that we use what? Sine. But remember, for current graph, we use cos. So, for this one, since it's a potential difference graph, let us look at this position. The coil is parallel to the magnetic field line. The normal line, the black line, is perpendicular to the magnetic field line, meaning that the angle between the magnetic field line and the normal line of the coil, it is 90 degrees. So, we're going to have sine 90 at this position. Sine 90, which is equals to 1, meaning that we're going to get a maximum value. The reason I'm not saying 1, some people may get confused and say, I said 1. Here, there's no 1 because we are not dealing with numbers at this point in time. So I'm going to say we're going to get a maximum value. By getting a maximum value, meaning that we're not going to get a 0, we're going to get the number which is the maximum here. So it means our graph is going to start from a maximum value, a number which is at the top, toper than 0, greater than 0. Then we turn the coil. Look what happened. I can even repeat that thing, that here we have 90, here we have 0 degrees or 360. As we do in math, here we have 270 degrees, here we have 180 degrees. So the first time, the normal line is at 90. When we turn it, the normal line is at 0 or 360. Because surely sine 360 will have to give us a 0. Let us check. It gives us a 0, it is true. So you can see here, whether you use 0 or 360 is the same. Now the normal line is at which angle? The normal line is at 0 degrees or 360, meaning that we're going to have what? Sine theta, which is sine 0. Sine 0 is 0. What does that mean? It means the voltage when the coil comes to this position, the voltage will decrease. Remember that the coil is always turning, right? It means that, I will show you on the video, it means that the voltage will be increasing, decreasing, increasing, decreasing, alternating in that way. So I'm just showing you very slowly how the coil turns. It started here, it turned to this position, whereby the angle between the magnetic field line and the normal line is 0. That's why I got sine 0. Then it turned again. Look at the normal line. The normal line, this summer line, it is pointing at 270. It is pointing at 270. Sine 270 will give us a -1. That's why the voltage will go to the negatives. Then, when it is at 270, it turns for the last time to 180. When it turns to 180, what will happen? What is sine 180? Sine 180 will give us a 0, meaning that the voltage is going to go up again to 0. It is going up to 0. Remember, it was here at the maximum value. Then it turned to 270 to 180, not 270. Sine 270, sine 180, 0. Then that's why it is returning here. Then it turned for the last time to the original position. Turn to this position, which is 90 again. So it means we're going to have what? Sine 90. What is sine 90? It's 1. We're going to get a maximum value. So we've drawn the graph. We've represented a graph from this position. Take a look at the normal line. Now the coil is perpendicular to the magnetic field line. You can see that this magnetic field line, they are perpendicular to the coil. But what about the normal line? They are parallel. So, since we're dealing with a volt graph, remember for voltage, what do we use? For voltage, we use sine. So it means we're going to have a sine theta, of which theta is the angle between the normal line of the coil and the magnetic field line. So since we're starting at this position, what is the angle between the magnetic field line which are parallel to this normal line? I've represented the normal line by a black thing. It means that the angle is 0. So it means we're going to have sine 0. What is sine 0? Sine 0 equals to 0. It means our graph is going to start here at 0. I hope you understood. Our graph is going to start at 0 because sine 0 is 0. Then, what will happen? Then our graph turns. When it turns, it will turn to what? It will turn to 90. Let me say it will turn to 90. It turns to 90. Then what will happen? When it turns to 90, our graphs will have sine 90. What is sine 90? Sine 90 is equals to 1. Meaning that it will go to the maximum position. Someone will argue and say it has turned to 270. It's still correct. That's why some people will start when they draw the graph for DC, it's either they draw it this side or they draw it this side. It is still the same thing. So you can start from the bottom. You can start like this. It is still the same thing. It's still the same thing. Okay, are we fine? Wow, good. Then, where is it? Oh, it started from here. Then it went to this, to 90. Then it turned to 180. Remember we use sine? Then you can see it points this direction, which is 180. If you just join now, just check, we're talking about this. 90, 0 degrees or 360 to 70. This time around, it started from this position. It started from 0, sine 0. Sine 0 is 0. That's why it started here. It turned to 90. It say it turned to 90. I'm saying that others can say it turned to 270, then they go down. It is still the same thing. There is no problem. There's no problem. You are correct. You can draw the graph starting from this side or this side. Myself, I prefer to draw it up. Okay? It went to 90, then it turned like this, coming to 180. Sine 180, sine 180, sine 180 is equal to 0, meaning that it will come down. It will become 0. Then, when it is at 180, it turns again. It turns to what? It was here. It turned to 270. When it turns to 270, sine 270, what is sine 270? Sine 270 will give us a negative 1. It will come down here. Then, lastly, it must return back to its original position. Its original position. 90, 0, 270, 270, and 180. It was at 270, turned to 180, became 0. Then it must return to its original position. The original position, which is 180. It is 180, it is like this. It started from here. When it is 0, sine 0 is 0. I'm sorry. Sine 0 is 0, it turned to 90. Sine 90 is the maximum position, is 1. Then 180, you can see, right? Then it turned again. Then it means this time around we return to what? To 0 again. We have returned to 0. So I hope you understood how we get to produce this graph. It depends on the position of the coil at the particular moment. But remember, there will always be a difference between an EMF graph and the current graph. Or I can just do a last demonstration. Last demonstration for current graph. Isn't it here we were dealing with the EMF graph? Let us do a last demonstration for current. Look at this. Here we're going to have current. Here we're going to have current. Here we're going to have time. Time which is in seconds. Then what do we do next? What do we do next? We start. Let's check here. We have a loop. North, south. Magnetic field line. Magnetic field line. Remember that for current we use cos theta. Theta, which is the angle between the normal line and the magnetic field line. So, in which position does start? Let me start from this position. Great. I'm starting from this position. What is happening now? The normal line is parallel to the magnetic field line. What is the angle between the normal line and the magnetic field line? The normal line is this black line, which I've just represented the normal line by 8. It means that the angle between the two is 0. What is cos 0? Cos 0 equals to 1. Cos 0 equals to 1. So it means we're going to have the maximum point. The maximum point. Let's say we are saying magnetic flux magnetic flux cos theta. By having a maximum point, I'm saying that when we write cos 0, we're going to get AB multiplied by 1. Meaning that if we have numbers where there's A and B, we're going to get the maximum value. That's why I'm saying it is going to be at the top. Then the coil turns. The coil started here. It turned. It is 90 now. Can you see that? It is at 90 degrees. So what do we do? It means we're going to say cos what? Cos 90 degrees will give us a 0. That's why it needs to, the current is going to decrease down. Because it started here, then it turned to what? To this 90 degrees. What do we mean? We are saying that the angle between the normal line and the magnetic field line is 90. That's why it becomes 0. Then it turned again. Can you see? It turned this side to 180. It turned to 180, 90, 0, 270. Can you see? It is at what? It is at 180. When it is at 180, what is cos 180? Cos 180 equals to negative 1. That's why it will go down. It will go down. Then it is at 180. Then what will happen? It turned. When it turned, it get to what? It get to 90. Some can say it is at 90 or it is at 270. It depends on what you want to call it. It is in this direction, 90 or 270. You can see that this line is either pointing downward or upward. What is cos 90 or cos 270 is 0, meaning that the current is going to go up again. Then we're in the last stage. In the last stage, it is returning back where it started. Just check. Then it will return back to where it started, returning back to 0. What is the angle between the magnetic field line and the normal line now? It is 0. Then we're going to get a maximum value just like that. Now, they will produce the graph for current and time. Electrodynamics. I hope you understood. The main thing is for you to understand the position of the coil, and that for voltage you use sine, for current you use cos theta. I'm speaking in this broken physics of for current we use is because certain things the exam guidelines say we must not teach, so we cannot just teach you the derivatives of these things. Those who are interested, those who are going to do physics, they will learn more about these things in the University of making the derivative. Okay, so now let us talk about the DC. The DC, which is direct current. Direct current. The graph of this one is straightforward. It does not alternate. It moves in the same direction, meaning that if it is for voltage, your graph must be like this. Your graph must be like this. Or if you don't want it to draw it at the top, if you don't want to draw it at the top, your graph can be at the bottom. Your graph can be like this, So it depends on how you want to draw your graph. The main important thing is to know where your